All right, for this lesson, we're going to be talking about different ways of factoring a quadratic. So when we look at quadratics, we are talking about that exponent of 2. And there's different, depending on how many terms it has, depends on how we would want to factor that. So what does factor mean? Well, factor means that you're basically breaking down the polynomial into smaller expressions. So you're going to be breaking down the polynomial into smaller expressions. Now we're going to want to do this because eventually when we get to the solving quadratics, you're going to have to do some factoring in order to get those pieces. So when we talk about breaking it down, that means that we're undoing the multiplication. So if something is being multiplied, that means we're undoing that multiplication. But the one thing and the most important thing really is you always have to check for a greatest common factor. There may not be one, but you need to check for one. So let's just kind of review what greatest common factor is. So greatest common factor is the largest number that you can basically take out of all the pieces, whether that be the numbers and the variables. So when I look, I should be able to see that I have 8 and 4. So the largest number I can divide out of 8 and 4 at the same time is 4. Now, I don't have a variable on this 4 term, so I can't take the m out, okay? I have to have a variable, and they have to have the same amount of variables on both pieces. So my GCF is the number 4. So that means if I divide 4 back out, okay, so essentially what we're doing is we're going to say 8m divided by 4. So that's going to leave me with 2m. And then we're going to be dividing 4 out of 4, and that leaves me with plus 1. So if you notice, what originally would have done is we would have distributed that, which gave us the 8m plus 4. So we undid that distribution, that multiplication. All right, so looking at number 2. So for number 2, let's start with the numbers. So I have 9 and 21. So the largest number that I can divide into 9 and 21 is going to be 3. And then I have variables this time. So this one has 2 p's, because remember p squared is p times p. And then I have a p here. So I can definitely take 1 p out of each term. So we're going to take 1 p out of each one. And my GCF is going to be 3p. So we're going to take 3p out, which means we're going to divide it out into the problem. So we're going to divide 3 and p. So 9 and 3 is going to give me 3. I had 2 p's divided by 1 p. That leaves me with 1 left over. So this is going to be 3p. So we're going to do the same thing here. We're going to say 3 and p. So we're going to say 21 divided by 3 is going to be 7. I had 1 p in that problem, and I took 1 out. So again, just remember when you're doing the variables, this is the same thing as p times p. So we're able to take 1 out of each term. We can't take more than 1 because we have to take the same amount. All right, so for the next one, I have 5x cubed and minus 10x. So just as a reminder, this is x times x times x. All right, so I have 5 and 10. So the largest I can divide out of 5 and 10 is 5. And then I have 3 x's, and then I have 1 x. So I'm able to take 1 x out of each one. So my GCF for this one is going to be 5x. So if I divide 5x back out of each term, that's going to undo that multiplication. So I'm going to divide 5x here. So 5 divided by 5 is 1. Now I had 3 x's, but I took 1 out, so that leaves me with 2 of them. So I don't have to write the 1 in front. I can, because if we did 5 divided by 5 is 1, but we should automatically know that any variable has a coefficient of 1 if we don't see it. So then we're going to divide negative 10 and 5. So that's going to give me negative 2. And then I had 1x, and when I divided that, I took an x out, so I'm left with none. All right, so this time we got 3 terms, so we've got to make sure whatever we take out all 3. So I have, in this problem, I have a 5, a 10, and a 5. So I know my GCF is 5. However, This, because it's in standard form, which means all the variables are going down from least to greatest, I have a negative in front. So I want you to get in the habit, whenever you have a negative coefficient, a leading coefficient, go ahead and take the negative out with the GCF. It's going to be helpful for you later on. So I don't know if you want to make a note here, but remove negative with GCF. Okay, so whenever I have a leading coefficient that's got a negative, I'm going to take that out with the GCF. And then I have, here I've got 3 m's, because it's 3 to third, or m to the third power. I've got 2, and then I've just got 1. So I'm going to take 1 m out of all 3 terms. So my GCF, we're going to make that negative 5m. All right, so if we take negative 5 and m out of each term, that means we're going to divide it out. So again, we're going to say negative 5 divided by negative 5, which is going to make that into a positive 1. And again, that's going to be more helpful for us later on. So I had 3 m's and I took 1 out, so I'm left with m squared. And then negative 10 divided by negative 5 is going to be plus 2. And I had 2 m's, but I took 1 out, so I'm left with 1. Negative 5 divided by negative 5, or 5 divided by negative 5 is going to be negative 1. And I had 1 m, I took 1 out, I'm left with no m's. All right, and this last GCF. So I've got, for my numbers, I've got 6, 4, and 2. So the largest number I can divide out of all 3 of them is 2. And then for my variables, I've got 3 x's here. I got 2 x's here. And then I've got 1. So we're able to take out 1 x from each term. So our GCF for this one is going to be 2x. So if we divide 2x out of each term, we're going to factor that GCF out. So 6 divided by 2 is going to give me 3. I had 3 x's, but I took 1 out, so that leaves me x squared. And then 4 divided by 2 is going to be 2. And then I had 2 x's, took 1 out, I'm left with 1. And then 2 divided by 2 is 1. I had 1 x, but I took that x out, so I'm left with no variables on that last term. All right, so as just a review for GCF, I hope that we need to make sure that we remember this every time we factor. Even if we don't have one, we always need to check. So the next thing that we're going to talk about is factoring with 2 terms. Now, even when we have 2 terms, we always want to check for a GCF before we get started. Now, when we do 2 terms, there is a method or a technique called difference of squares. So this difference of squares is called difference of squares for a reason, because they have to have certain criteria in order to factor it this way. So when I have difference of squares, okay, first thing that you got to make sure of is difference of squares can only happen when I have 2 terms. So 2 terms means 2 pieces, whether it be variables, numbers, or a combo of both, separated by addition or subtraction. So I need 2 terms. I have to have perfect squares. So perfect squares are those numbers where it's like 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and so forth. And we'll go over a few of those in a minute. And the last thing is it's called difference of squares because it has to be subtraction. Okay, it has to be subtraction. So it can only be 2 terms. It has to have perfect squares, and it has to be subtraction, which is why it's called difference of squares. Now, just to make a note, this technique that we're going to talk about does not work with sum of squares. This is only a technique that works. It's like a shortcut for factoring. The sum of squares is non-existent. It does not work when we have addition. It has to be difference. So how does it work? So when I'm looking at a problem, if I have two terms, so this is my first term, this is my second term, and I have both of them as perfect squares, then I can break those squares down, okay? And I'm going to break them down, and I'm going to take the square root. So if I take the square root of a squared, I have a. So the a that we're talking about, that's going to be put in the first part of the term, because a was in the first part of the term when we had, or the expression when we had it initially. Okay, so we're going to break that down by taking the square root, which is why it has to be a perfect square, so we can take the square root of it. So then we have our b squared. So b squared, whatever that may be, is a perfect square. So we take the square root of that and we break it down into two b's. So we have a b, and we're going to put that in the second part because it was the second term in the problem. Now, the last thing that's super important is the fact that it needs to be one positive and one negative. That's the only way that this works out, because when we multiply it out, we need to have a positive and negative so those middle pieces cancel and leave me with two terms. Okay, so with that being said, let's talk about our perfect squares. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared, 25, 6 squared is 36, 7 squared is 49, 8 squared is going to give me 64, 9 squared is going to give me 81, 10 squared is 100, 11 squared is 121, 12 squared is 144, 13 squared is going to be 169, and then 14 squared is going to be 196. Now these can keep going, but these are just like the top ones that we see the most. So what we're going to be looking at, so when we look at number 6, I have two terms. My first term is going to be the 49x squared, and my second term is the minus 1. Now, if we look at this, first thing I'm always going to check for is a GCF. Well, 49 and 1, obviously I can divide it by 1 and make the 1 GCF, but I don't want to divide it by 1 because that's not going to change anything. So I have subtraction, I have two terms, and the last question is, are they perfect squares? Well, 49 is a perfect square because 49 is technically 7 squared. 1 squared is a perfect square because that's 1 squared. Now, the last thing comes down to the variables. So any even exponent is a perfect square, because I can say x to the 6 is the same thing as x to the third times x to the third. I can break it down into halves, which is what you're doing when you multiply exponents. You add them together. So how does this work? We're going to create two parentheses, one plus and one minus. So you got to remember that. You always have to have one plus, one minus. I don't care if you put the minus first. It doesn't really matter. But what we do need to do is we need to take 49x squared, and we need to take the square root of that. So if we take the square root of that, that's going to leave me with 7x. So the 7x, because the 49 was in the first term spot, is going to go in the first term spot in both parentheses. Then we're also going to take the square root of 1. So the square root of 1 is still 1. That's going to go in the second spot. Okay. Now, why does this method work? Because if I were to multiply these two things back out, so I'm going to just kind of show you my little box and multiply it out. So we got 7x and 1, 7x and negative 1. So that's going to be 49x squared. That's going to be negative 7x. This is positive 7x. And this is negative 1. And these two are going to cancel each other out, which is why we have to have a plus and a minus. So because they cancel each other out, I'm only left with 49x squared minus 1, which was the original problem over here. All right, so for number 7, we have two terms, and this time I have addition here. So it doesn't look like it's difference of squares. However, I need to check for a GCF. So if I look for a GCF, I have negative 50 and 8. So if I'm thinking about what's the largest number that I can divide into both of those, so I definitely could divide 2. can't divide 4, can't divide 8. So I do have a GCF of 2. However, we said just a second ago that if I have a negative as my leading coefficient, I want to go ahead and take that negative out with the GCF. So if I say negative 50 divided by negative 2, that's going to leave me 25, positive 25, and the x squared because we weren't able to take out any variables. Then I'm going to do 8 divided by negative 2, which is going to leave me with negative 4. And once I do that, I now have in the parentheses a difference of square problem. If you look, I now have subtraction. 25x squared is a perfect square, and so is negative 4. So if I take the square root of my 25x squared, that's going to leave me with 5x. So when we write this out, that GCF does not go away that we took out. It's still part of the problem, okay? So we're going to do 2 parentheses, and we're going to do 1 plus and 1 minus. So the first one we got was a 5x. That was in the first term spot. So we're going to put 5x and 5x here. And then we're also going to take the GCF of 4. So the GCF of 4 is going to be 2. So that's going to go in the second spot of both parentheses. And again, if I multiply this out, I could distribute this in, get a different numbers in that term, and then multiply it, and it would give me this same original polynomial or quadratic that I had. All right, so for number 8, again, we always check for GCF first, and I should see that I have 144 and 16. 144 is divisible by 16, so 16 would be the largest number. So if I pulled up Desmos, just to kind of check it out, I can see 144 divided by 16 does in fact give me 9. Now, that means that I'm going to divide 16 out of all of the terms. So if I do 16 here, that's going to be 9y squared. And then 16 divided by 16 is going to be minus 1. Now, what we should see is after taking that GCF out, we now have the difference of squares inside the parentheses. So the 16 is not going to go away. It's still going to be part of the problem. But I can now computate the difference of squares for each term. So I have 9y squared. If we take the square root of that, that's going to give me just 3y. So remember, when you make your 2 parentheses, you're going to do 1 plus, 1 minus. And it doesn't matter if you put the plus first or the minus first, as long as there's one of each. So we're going to put 3y in the first term spot in both parentheses. We're also going to take the square root of 1, and the square root of 1 is also going to give me 1. All right, so then for number 9. Now for number 9, sometimes it confuses students just because of the fact that they're so used to the variable being written on the first term, but it doesn't matter because they're still perfect squares. So do I have a GCF for this? So 49, we can't divide it by 9. We can't divide it by 3. So at this point, there's no GCF here. So we're just going to go ahead and look. We have 2 terms. We have subtraction. 49 is a perfect squared, and 9y squared is a perfect square. So we're going to do difference of squares. And when we write this, we need to make sure we get 1 plus, 1 minus. All right, so we are going to take the square root of 49, and the square root of 49 is going to give me 7. So 7 is going to go in the first place, in the first part of the parentheses, just like the 49 was in the first, it was the first term of the actual expression. All right, and then we're going to take the square root of 9y squared, which is going to be 3y. All right, so once I do that and I get 3y there, we're going to be able to put that into the second part of both parentheses. So we have 7 plus 3y times 7 minus 3y. So don't change up the order just because the variable doesn't look right in the second spot or the second term. All right, so if we have two terms, always check for a GCF and then see if you have difference of squares. Now, if you don't have difference of squares and you're able to take out a GCF, then you can't factor any further. We do have some factoring later on that's like difference of cubes and all that, but for right now, we're just focusing on difference of squares.